Hi Finn, thanks for your email. So, if I can help, so the electromagnetic spectrum, okay, are the various waves that exist, okay, and they all have different wavelengths. And the shorter the wavelength, the higher the frequency, which means how many times it oscillates per second. So, if you have, for example, this over here, we have really short wavelengths, okay? These are the gamma rays, and they're really high energy. In fact, gamma rays is radiation which causes damage to human cells, so really high energy. X-rays, as you know, you can only have a certain number of X-rays as a result of the fact that they are bad for you and can give you cancer, okay? Ultraviolet is what bees see, and you can see the wavelength is getting longer here as we go along. A slightly longer wavelength, and you come to visible light, which is the colours of the rainbow. Richard of York gave battle in vain. Okay, so they're the colours of the rainbow. Then we come to infrared, which is a slightly longer wavelength. Microwaves, slightly longer. And then radio waves are really, really long. Okay, so they are 10 to the 3 meters is 1 kilometer. Okay, so in this we have a spectrum of waves, and waves are all capable of being reflected and refracted. They all behave in the same way. Now, the ones of a real interest to us are these ones, the visible light, because this is what we can see. We have evolved to be able to pick up this particular bracket here of visible light. So in a room, there are loads of ultraviolet rays zooming around. There's infrared being released from anything that's got a temperature. You might have some microwaves that escape from your microwave oven. You've definitely got radio waves going through, but it's these guys, the visible light, that we can pick up. Okay, so if we go on to specifically how that works, we have a wave, and what's going to happen is this wave is going to hit something and be reflected or refracted, for example. Okay, so about waves, we need to know a couple of terminologies. Okay, we need to know that this is the amplitude, okay, which is from the midline up to the top, or this is the amplitude from the midline to the bottom. It's not the whole from the very bottom to the top. Okay, and we need to know that from a crest to a crest, like that, is the wavelength. Okay, and we need to know frequency, by the way, is how many waves per second. Okay, so if this was time 0, okay, and this was 1 second, then we can see that is 1 wavelength, and so that will be 1 wavelength per second, and we call that 1 hertz. Okay, so that is our basics on a wave. And so what happens when these waves are reflected? Well, it's actually very simple. Just to put it into context of what we're doing, this is what this would look like, actually, this line, but we just make it a line, so that's fine. Okay, so it makes it much easier. Okay, and what we have is that wave will hit a mirror, and all you need to know is that the angle of incidence equals the angle of reflection. Okay, so that angle here is equal to that angle here. Okay, and that's all you really need to know. So if you were asked, if they said that the angle R was 35 degrees, okay, actually that's degree C, sorry, and this then, and what was I, then I is 35 degrees. And the way you do it is that this line here is called the normal, and that is always the line that is at 90 degrees to the surface. So if the mirror was like this, the normal would be 90 degrees there. See, that's 90 degrees. If the normal was like this, then the normal would be there. That's 90 degrees. Okay, and so if we did have on one of those surfaces a light ray that came in like that, we know that that angle must be equal to the angle of reflection, which is that angle, and so I, which is the angle of incidence, equals R, the angle of reflection. Okay, and it really is that easy. And so that is what you need to know about reflection. Okay. If you are needing to do a scale diagram, okay, you need to use a protractor, but all you need to really know is the angle of incidence is equal to the angle of reflection. Okay. Now, the thing about this is that I'm just going to draw here in, say, blue again. We can actually be fooled when we look in a mirror into thinking that if you look in a mirror, you've got used to knowing it's a reflection. But actually, if you're here, okay, so here's your eye. As you look at a mirror, it kind of looks like your face is here. Okay, it's like there's another person on the other side of the mirror, isn't there? And we know it's a reflection. So, but 2,000 years ago, they might have thought that was some kind of witchcraft or something. So that's an optical illusion, effectively. It looks like somebody is on the other side of the mirror. And why does that happen? Well, this is the diagram which shows you how that happens. Okay, so light always comes from an object, and when it comes to a mirror, it comes along here, it's reflected into your eye, okay, which receives it here like that, okay, and the way that you would do this is you would draw the ray diagram there, okay, just because that's the way it would be, and the way you'd know that, if I just make this a bit finer. So let's say, so can you see, here's my mirror, so that's the surface, so my normal is there at right angles, my normal is there at right angles to the mirror. So this angle I is equal to R, and this angle I is equal to R. So if you were given these two rays, number one and number two, you can see the way that they've hit that. You draw the normal and you work out that one there. For example, you measure it with a protractor, and that one there, and then you make this one there exactly the same. Okay, and then that gives you the rays going back to the eye. And then what you do is you go, okay, that's the rays coming to the eye. For a mirror, it looks like the image on the other side. And then what you do is you just carry on these lines until they converge and make a point. And then that is where the image appears to the eye. Okay? It's a bit complex, but it's a case of just remembering how to draw the ray diagram. So you do a normal ray diagram reflecting off the mirror, and then you take the rays from the eye and carry them on past the mirror to create an image here. Okay, so I hope that helps in terms of those the rays, waves, and how light reflects. Okay, there is refraction, which is bending of light here, and that is where the reason that happens is that this is air and this is glass, and glass, as you can imagine, is more dense than air. So imagine the light waves coming in, and they're going really fast because they travel so fast in air, and then when they get to the glass, they're slowed down. And the way that manifests itself is that instead of carrying straight on, so they would have done that, they actually bend. Okay? And then when they come out, instead of carrying straight on, because air is less dense than water, they speed up again and they bend. Okay? And so refraction happens because light waves change speed when they're entering or leaving a more dense material. And the last thing to say about this, Finn, is that when you are going into a more dense, when you're going into glass, so air going to glass equals a bend towards the normal. And glass going to air goes to away from the normal. Now, what does that mean? Well, here is our normal, okay, and look, that light would have gone that way, but it's come down towards the normal when it's gone into the glass. And this light would have gone there, but look, when it's gone out back into the air, it's away from the normal. So if you can remember air, glass, air, as it goes away from the glass, it bends away from the normal, so you can remember which way is which. Okay, I hope that helps, and keep going. Okay, and send me any other details you need if you need me to go over anything or you have any questions. Take care. Hope you're well.